Chapter 23, the Respiratory System. So the respiratory system, of course, is going to talk about how we distribute oxygen to our tissues and then take CO2 as a waste from those tissues and rid it from the body. Our cells get energy primarily through aerobic metabolism, aerobic meaning with oxygen. So it's going to require oxygen and then produce carbon dioxide. Oxygen is obtained from the air by diffusion across the exchange surfaces in the lungs. And that's going to be referring to our alveoli, which we'll get to a little later. Blood carries this oxygen from our lungs to our tissues, and then will carry carbon dioxide from those tissues back to the lungs so that we can exhale it out. The functions of your respiratory system are to give extensive surface area for gas exchange between the air and the circulating blood. And this again is going to be down at the alveolar level. We're going to move air to and from those exchange surfaces in the lungs. We have parts of the respiratory tract that will protect respiratory surfaces from dehydration, temperature change, and also pathogens. We make sounds through our respiratory tract, specifically our voice, and we detect odors with olfactory receptors in the nasal cavity. So our sense of smell also lies in the respiratory system. We can divide the respiratory system into an upper respiratory system and a lower respiratory system. The upper respiratory system is going to include the nose, nasal cavity, sinuses, and also your pharynx. The lower respiratory system begins at the larynx, moves through the trachea, bronchi, bronchioles, and finally the alveoli. So let's take a look at that in a picture to get a full visual. So we've got our dividing line right here. So right at the larynx is where we have the beginning of the lower respiratory system, and then above the larynx would be our upper respiratory system. And we do divide these because each section of the respiratory system has a different function in breathing. So again, upper respiratory is going to include the nasal cavity where the air comes in. We then have the opening up of the nasal cavity. So we're coming through the nose into the nasal cavity. We have the sinuses here and also here. And then the pharynx, which is here. And starting right here at the larynx, we have the lower respiratory system. So that would be the larynx, trachea, bronchi, which go into each lung, the lungs themselves, and then we branch into finer and finer branches called bronchioles, down to the very ends, which are filled with alveoli. Here. The respiratory tract is the conducting portion of the tract, and this goes from the nasal cavity down to the larger bronchioles. So this would be basically where the air comes in, and we conduct that air down all the way to these bronchioles. And then we have the lower respiratory portion, which is the smallest respiratory bronchioles and the alveoli. So that would be when we get down to these really fine branches, which will end in the alveoli. That's where we're going to actually exchange gases. The alveoli are the small air-filled pockets within the lungs. There are about 150 million per lung, and this is where all gas exchange takes place. The respiratory mucosa is what lines the conducting portion that we just looked at of the respiratory system. It's made up of epithelial tissue, which remember lines and covers body surfaces, and areolar tissue, which is a thin layer underneath that epithelium. The respiratory defense system is made up of a series of filtration mechanisms that are going to help us to get particles and pathogens out of the inhaled air. Because unfortunately, the air we breathe in is not pristine, so there are some things that have to be filtered out to prepare that air for the lower passageways. So this is the surface of the epithelia in the respiratory tract, and you can see that it's covered with a shag carpet of cilia. And this is helpful because this cilia is going to sweep mucus across these epithelial surfaces. So if we have things that are undesirable that get into the respiratory tract, hopefully the mucus would trap those items, and then we could sweep those items out of the lower passageways. So we're going to go into that a little bit more in just a few minutes. Here's a close-up view of the epithelium in the respiratory tract, and it shows the epithelial tissue here and also these goblet cells, which are producers of mucus. So you can see the mucus is produced and is coating the cilia. And the cilia is, of course, sweeping upward. And you can see that the mucus has trapped some particles in it. And so we're sweeping that up from the respiratory system up to the back of the throat, or your pharynx, where you can then swallow that mucus. And anything caught in it will hopefully be destroyed by stomach acid. So again, we'll come back to that and kind of line it up in the full picture of the respiratory defense system. Alveolar epithelium is what's going to line the delicate exchange surfaces of the alveoli. It is very delicate, simple, squamous epithelium. So we hopefully remember that simple squamous or squamous, that means one cell layer thick, very thin, and also squamous or squamous means irregular shape, thin cells. And so the simple squamous epithelium here makes a lot of sense because we are trying to diffuse gases across the alveoli, so we would like it to be nice and thin. We also have some scattered specialized cells throughout the alveoli as well, and we're going to take a look at that as we get a little closer to the alveoli. So we're going to kind of hold off on those cells until then. So back to the respiratory defense system. The respiratory defense system begins with filtration in the nasal cavity. This is going to remove large particles that we inhale. There are mucus cells and mucus glands that will produce mucus that keeps that nasal cavity nice and coated in mucus. And we've also got nose hairs, right? So when we breathe, the air has to go through the nose hairs, which can trap some particles, and then into the mucus of the nasal cavity, which can also, because of its stickier nature, can trap some large particles as well. And if any of the particles get past the nasal cavity, it can get caught in the mucus in the pharynx or larynx, and then that cilia can sweep the mucus up towards the pharynx to be swallowed. We also have alveolar macrophages. So our first line of defense, nose hairs. Second line of defense, if anything gets past the nose hairs, it gets caught in our mucus escalator that's coming up from the lower passageways towards the back of our throat, where we will then swallow it and zap it with stomach acid. And then our third line of defense is the alveolar macrophages. And these are cells that will engulf small particles that make it all the way down to the lungs. So they're the last chance to catch things that could cause infection. So if something gets past all three of those defenses, then we will likely get sick. But we're going to try to trap bacteria and other things that come in with this defense system. The nose is where we begin, and this is the primary passageway for the air that comes into the respiratory system. The air is going to enter through the nostrils, which are more officially known as the nares, and then pass into the nasal vestibule. This is the space within the flexible part of your nose. Nasal hairs are in the epithelium of the vestibule, and they'll trap the large particles. So going forward to this picture, you can see the air would come in here through the nostrils, which has the nose hair, then into the vestibule, which is the flexible space in the nostrils, and then we're going to head this way. So when we head that way, we are going to hit the next little part, which is the opened area of the nasal cavity. So we're going to look at some of that anatomy as well. The nasal septum is going to divide the nasal cavity into a left and right side. So just like you clearly see, you have a left and right nostril. The septum is the division in between those sides. And the top part of your nasal cavity, superior part, is where your olfactory region is. So this, when air comes in, it's going to move against that superior portion of the nasal cavity and give us a sense of smell. And mucus that's made in the sinuses and tears will help to clean and moisten our nasal cavity. So let's look at the septum before we go on. In this picture, we have a frontal cut. And so orienting you to the picture, we've got, of course, an eye there, the roof of the mouth, also known as the hard palate, and then the tongue here. So this area represents the nasal opening. And what you should notice is right here in the middle, this is the nasal septum. And the nasal septum is made up of two bones, and these would have been bones you learned in Anatomy 1. We have the perpendicular plate of ethmoid, and then down here we have the vomer. So the union of these two creates the nasal septum. Okay, so air will flow from the vestibule, that flexible part of your nose, to the choanae. And the choanae are the openings that lead to the actual nasal cavity. And we'll take a look at that as well, openings in the nasal cavity. We're going to move through the superior, middle, and inferior nasal meatuses. I'll show you what those look like. Meatuses are passageways. They're very narrow, and they're going to help us create turbulence, to help trap particles in the mucus, to warm and humidify incoming air, and to bring olfactory stimuli to olfactory receptors, so we have more time to figure out what we smell. Okay, so looking here, as air comes in, it goes through the nostrils and the vestibule. We're passing into the large nasal cavity. And you can see these three things here. This is the superior, middle, and inferior meatus on one side of the nasal septum. Of course, you'd have another set on the other side. But as air comes in, I kind of like to think of this sort of as speed bumps. This is going to greatly slow the air down as we hit these narrow passageways. And by passing through these narrow passageways, we are going to be able to slow the air down enough to try to filter it a bit, humidify it some, and also allow us time to really smell what is in the air. Once we go past the speed bumps, we head into this area called the choanal, and the choanal is this opening here that leads us to the pharynx. Okay? So the hard palate forms the floor of the nasal cavity and separates the nasal and oral cavities. We'll look at that too. And the soft palate extends posterior to the hard palate. And it's helpful because it shows us where the division between the nasopharynx and the rest of the pharynx is. So let's look at that also. So here's our pharynx. And we have the top part of it is going to be our nasopharynx because it's behind the nasal cavity. Middle part is the oropharynx, which is behind the oral cavity. That makes sense. And then the bottom portion is the laryngopharynx, which is right near the larynx. Also makes sense. Here's our hard palate, which is made of the maxillary and palatine bones. And they are separating the nasal cavity from the oral cavity. Coming off of the hard palate is our soft palate, which is soft. It's made of cartilage, not bone. And that's our dividing line between naso and oropharynx. The nasal cavity opens into the nasopharynx at the choanal, which we pointed out here. The nasal mucosa, so this would be the epithelial tissue that lines the nasal cavity, is going to warm and humidify that inhaled air for arrival at the lower respiratory system. If you breathe through your mouth, you do bypass this very important step. And nosebleeds are common because there is a lot of vascularization in the nasal cavity. Lots and lots and lots of blood supply in the nasal cavity. The pharynx is what we just looked at. That's the chamber shared by the digestive and respiratory systems. It extends between the choanal and entrance to the larynx and esophagus. It's divided into three parts, which we just pointed out, called the nasopharynx, oropharynx, and laryngopharynx. As we showed in our last picture, the nasopharynx is the superior portion of the pharynx. Oropharynx connects directly to the oral cavity, and the laryngopharynx is our last section between the hyoid bone and the entrance to the larynx and esophagus. So that's our lowest one, nearest the larynx that we looked at before. So as the air goes down to this point, we're at the laryngopharynx. We're going to move into the larynx. And this is the beginning of the lower respiratory system. We're going to go through the larynx through a slit-like opening between your vocal cords called the glottis. The glottis is going to open for air to go in. And there are three large unpaired cartilages that help to form the larynx that we're going to look at: thyroid, cricoid, and epiglottis. So the thyroid cartilage is hyaline cartilage. We talked about that in Anatomy 1. This is a similar cartilage to what you find lining the joints. It forms most of the front or anterior and the side or lateral walls of the larynx. The anterior surface is called the laryngeal prominence or the Adam's apple, which everyone knows it as. So let's take a look at that. So here is your larynx, and this guy right here in the front, the biggest one, this is your thyroid cartilage, also known as the Adam's apple. And it is called the thyroid cartilage because the thyroid lies very close to it, which we saw back in chapter 18. Okay, and then we've got the cricoid cartilage, which is also hyaline. And it's going to form the posterior or the lowermost portion of the larynx. So here is the cricoid here, And it actually wraps all the way around to the back. So you can see the biggest part of the cricoid is in the back or posterior. And finally, we have the epiglottis, which is an elastic cartilage. So it's a lot stretchier. And its job is to cover the glottis when you swallow. And this is going to prevent liquids and foods from going down into the respiratory system, which we know is called choking. It is not very fun. So we're going to take a look at that too. The thyroid and cricoid cartilages will support and protect the glottis, which is the entrance to the trachea, where our vocal folds are as well. And during swallowing, and you can feel this if you touch your own Adam's apple while you swallow, the larynx elevates and the epiglottis will fold over the glottis, preventing food and liquid from entering the respiratory tract, which is certainly helpful. So looking at a back view, this is a posterior view of the larynx. We have the epiglottis here, which looks like a little trap door, and it will fold down over the glottis when we swallow. So here's a side view or a lateral view. There's our epiglottis, little lid, little trapdoor lid, and it will lay down and cover up the vocal cords and the glottis when we swallow. So let's go back to the picture that showed the oral cavity, and we should be able to see that a little bit better. So here is the epiglottis, and you can see this is our larynx, and this is our trachea, and then right behind it is the esophagus. So this is where you do want food and liquids to go. So when we swallow, this little trap door will come down and close right there. So that's going to shut off the respiratory tract, but allow the liquids and food and saliva to head down this way into the esophagus, which leads to our digestive tract. When we are breathing, however, the epiglottis opens up like this so that air can come in and pass down into the respiratory system. So the epiglottis has a very, very important job. Okay? So moving forward to the vocal folds, sound production is air passing through the glottis, vibrating the vocal folds, which will produce sound waves. Speech is produced by phonation, which is sound production at our larynx, and also articulation, which is sound modification using our lips, tongue, and teeth. So this is what's going to cause the uniqueness in the human voice. So looking down into the larynx, here is the glottis, and it's closed in this picture. You can see the vocal folds very clearly, which we call our vocal cords. And this is when the glottis is open, leading into the trachea. So when we're breathing, the glottis is open for air to go in there. And when we're talking, we push air out through the glottis. And these vocal folds will vibrate, producing what we call sound that makes our voice. The larynx is associated with two sets of muscles. The muscles of the neck and pharynx, which help position and stabilize the larynx, and then smaller intrinsic muscles that control the tension in your vocal folds and will open and close the glottis. So once we leave the larynx and the air goes through the glottis, we need to head into the trachea, which is also known as the windpipe. The trachea is a tough, flexible tube that extends from the cricoid cartilage, remember that one, to the mediastinum. Let me remind you what the mediastinum is. The mediastinum is a central tissue mass that divides the thoracic or chest cavity into a right and left pleural cavity or lung cavity. So the trachea is going to go from the cricoid to the mediastinum and then branch into a right and left main bronchus. The trachea has 15 to 20 C-shaped tracheal cartilages. These are going to stiffen the tracheal walls to protect your airway, keep it nice and open. And they don't fully close, these rings, these C-shaped cartilages don't really close where the trachea contacts the esophagus, because the esophagus needs room to kind of spread out as we're swallowing. So I'll show you why and how that looks in just a second. So here's our larynx. We begin the trachea at the cricoid cartilage. The trachea passes all the way down and then branches into a left and a right bronchus. Each bronchus heads into a lung. So these rings of cartilage, they're C-shaped, meaning they come around like a C, but they do not connect in the back, so they're not perfect circles. If we look at a cross section, a transverse section right here, this is what we would see. So here's our trachea. This is the lumen, which means the hollow inside. This is where the air would be moving. And then here's our C-shaped cartilage holding the trachea open. Behind the trachea is the esophagus. This is where our food and liquids and saliva go. So when you swallow a large ball of food, or a bolus as they call it, the esophagus needs to expand with that food as it goes down to the stomach. Well, imagine if you had a complete circle of cartilage here. That bolus would bump against each cartilage ring on its way down to the stomach, which would be unpleasant. So because we don't have a complete cartilaginous ring here, this will allow the esophagus to expand a bit into this area without distorting the trachea. So once the trachea branches into bronchi, we call that the bronchial tree. The right main bronchus and left main bronchus will further divide to form lobar bronchi that supply the lobes of the lung. The lobar bronchi branch to form segmental bronchi, and each segmental bronchus will supply air to one bronchopulmonary segment. The right lung has 10 and the left lung has 8 or 9. So the right lung's just a little bigger than the left lung, so that it can, the left lung is a little smaller to make room for the heart. So let's take a look at that in a picture. So in this picture we can see where the trachea comes down and branches into a large left and right bronchus. The left and right bronchus then branch into lobar bronchi. So that would be like this gold here and the blue here. Each one of those is going to serve a lobe of the lung. On this side, because we have 3 lobes, we can see gold, green, and blue. And then we're going to branch even more finely to form the bronchopulmonary segments, which will get finer and finer and finer, and we'll go into how much finer in just a second when we continue going down the bronchial tree. The carina of the trachea is this ridge here that separates the openings of the right and left main bronchi at their junction with the trachea. So that little guy right there is the carina. We've got that mention of that here in our notes as well, that ridge that separates the opening of the right and left main bronchi. Okay, so as we're moving down from the segmental bronchi, which we just looked at from the bronchopulmonary segments, we're going to get even smaller. We're going to go down to the bronchioles, which are even finer, terminal bronchiole, respiratory bronchiole, and then alveoli, a cluster of alveoli. Okay, so again, bronchioles, terminal bronchiole, respiratory bronchiole, and a cluster of alveoli. And remember, there are about 150 million alveoli per lung. So this boxed in area, this purple area, this is considered the bronchopulmonary segment. The smaller bronchi, bronchioles, terminal, respiratory bronchiole, and alveoli in a cluster, which is called a lobule, all of this is considered the bronchopulmonary segment. And when we were up here, we talked about the carina, the main bronchus, which divides into lobar bronchi, and then smaller segmental, followed by bronchioles and down. If we zoom in on this bronchopulmonary segment, we can see a little closer what's going on here. So this is a single pulmonary lobule, which is a cluster of alveoli. You can see that they are little hollow sacs. And the alveoli are surrounded by capillary beds, which is very helpful because this is how we're going to be able to get the oxygen into the blood very quickly and the CO2 out. We've also got some bands of elastic fibers, which give the alveoli resiliency and expansion and contraction ability. So this is a microscopic view of lung tissue showing the organization of the alveolar sacs. And if we remember the autonomic nervous system, or ANS, this is the one that will that houses the sympathetic and parasympathetic nervous system. And we talked about how sympathetic is fight or flight, and parasympathetic is rest and digest. So the autonomic nervous system can also control your respiratory rate. It can control the diameter of the bronchioles by regulating smooth muscle, and controls the airflow in the lungs as well. Bronchodilation is caused by sympathetic activation. It enlarges the diameter of the airway, enlarges the lumen, and reduces resistance to airflow so we can breathe better, more air in at a time. Bronchoconstriction is when we reduce the diameter of the lumen of the airway, which can be caused by parasympathetic activation or histamine release, like an allergic reaction. The alveolar cell layer consists mainly of simple squamous epithelium, which is formed by thin, delicate pneumocytes, type 1. This is where gas exchange happens, and patrolled by alveolar macrophages, which is we talked about before. These guys are the ones that help to engulf invaders, and contain large scattered pneumocytes type 2, also known as septal cells. They produce surfactant. Surfactant is an oily secretion that has phospholipids and proteins in it. It will coat the alveolar surface and help to reduce surface tension so that the alveoli do not collapse. So here's a close-up view of the alveolar structure. We can see the individual alveoli. You can also see the capillary bed surrounding the alveolus. There is an alveolar macrophage patrolling the epithelium. These simple squamous cells are pneumocytes type 1, and then pneumocyte type 2 are these yellow cells called septal cells, and those are the ones that produce the surfactant. Gas exchange occurs across the blood-air barrier of the alveoli and which consists of 3 layers. The alveolar cell layer, that's our simple squamous epithelium, the capillary endothelial layer, and then in between, they're fused. So these guys have become as one, which is wonderful because it makes diffusion so instantaneous. So what we're looking at here is the wall of the capillary wall, and then we've got the alveolar wall here. In between is a fused basement membrane. And that fused basement membrane allows these two guys to literally like grow into one another so that gas exchange is instant. We breathe in, oxygen diffuses onto the red blood cell, CO2 diffuses out, we breathe out very, very fast. Gas exchange across the blood-air barrier is very quick and efficient because, as we just said, the distance for diffusion is very short. And oxygen and CO2 are very small and they're lipid soluble, which means they're able to get through that surfactant that's coating the alveoli. Left and right lungs are in the left and right pleural or lung cavities. The inferior or bottom portion or base of the lungs rest on the diaphragm. The lobes of the lungs are separated by deep fissures. The right lung has 3 lobes, superior, middle, and inferior, and are separated by horizontal and oblique fissures. The left lung has 2 lobes, superior and inferior, separated by an oblique fissure. So let's take a look at that. So here's our left lung. 2 lobes, superior and inferior. There's our oblique fissure. Here's the right lung, superior, middle, and inferior lobe, separated by a horizontal and oblique fissure. You can see that the right lung is bigger than the left, like we talked about. It's displaced upward a little bit by the liver, and the left lung is longer than the right lung, but has that indentation we pointed out before called the cardiac notch on its medial margin, so where the heart would kind of press in to the lung. The hilum is where the pulmonary vessels, nerves, and lymphatics enter the lung. The root of the lung is the big complex of dense connective tissue, nerves, and vessels in the hilum. It's also anchored to the mediastinum. Okay, in this picture you can see the diaphragm, and above that we see the right lung, which definitely looks larger than the left lung. There's our cardiac notch. And this is the inside or medial surface of the lung, where you can see the hilum. So the hilum again is going to be where the vessels, nerves, and lymphatics enter the lung. There are 2 pleural cavities separated by the mediastinum, as we talked about before, and each pleural cavity contains a lung. The cavity is lined with a serous membrane, which is called the pleura, and this is similar to the setup in the heart that we went over. The pleura has 2 layers. Parietal pleura, which lines the inside surface of the thoracic cavity, so parietal is the lining of the thoracic wall. Visceral pleura is what sticks to the lungs itself. In between is pleural fluid. Pleural fluid. Respiration includes 2 processes. We have external respiration and we have internal respiration. External respiration is all the processes involved in exchanging the gases O2 and CO2 with external environment. Internal respiration is the uptake of the O2 and the release of CO2 by the cells, which is the result of cellular respiration. There are some steps in external respiration. We have pulmonary ventilation, which is fancy for breathing. gas diffusion across the blood-air barrier in the lungs, across the capillary walls in other tissues, transport of O2 and CO2 between the alveolar capillaries and between the capillary beds and all of your other tissues. So the overview would be this. We breathe in and air and gases go into the alveoli. Oxygen diffuses from the alveoli into the blood. Red blood cells carry that oxygen to our tissues where we drop it off. The tissues are happy because they've received oxygen, and they send their waste in the form of CO2 onto the red blood cells, which carry it back to the lungs, and then we exhale that CO2 back out into the environment. So that's a very simplified view of the cycle. Pulmonary ventilation is breathing. That's the physical movement of air into and out of the respiratory tract. Provides alveolar ventilation. And atmospheric pressure, or ATM, is defined as the weight of the Earth's atmosphere around us. It compresses our bodies and everything around us and has several important physiological effects. Boyle's law. Boyle's law is going to define the relationship between gas pressure and volume, which is going to be very important in the process of breathing. Boyle's law is a law that states that the pressure of a given mass of an ideal gas is inversely proportional to its volume at a constant temperature. In a contained gas, external pressures will force the molecules closer together. The movement of gas molecules will exert pressure on the container. So what in the heck does that mean, and how does it apply to breathing? So let's look at a figure to try to help us figure this out a little bit more. So here is a container that has in it gas molecules. And you can see with the red arrow that represents the gas molecules bouncing off and colliding with the inside of the container. If we take this same container and decrease its volume, so we make it smaller, the collisions of these gas molecules will happen more often because there's less room for them to bounce around, so they're going to hit the walls more often. This is going to increase the pressure of the gas. If you increase the volume, so we make the space larger, the gas molecules have more room, so fewer collisions will happen. And because of that, the gas pressure inside the container will go down. So we can summarize this by saying, if we decrease the volume of an area or container, pressure will go up. If we increase the volume of an area or container, the pressure will go down. Okay, so we are going to tie that back to breathing. So we do need to remember Boyle's law because it's going to be a part of pulmonary ventilation or breathing. So pressure and airflow to the lungs. The rule is that air flows from an area of higher pressure to an area of lower pressure. A respiratory cycle consists of an inspiration, which is when we inhale, and an expiration, which is when we exhale. Pulmonary ventilation will cause volume changes that create changes in pressure. The volume of the thoracic cavity will change when we expand or contract our diaphragm or rib cage. So let's look at this in a picture, and this is going to tie back to Boyle's law. So we're looking here at the thoracic cavity, which is our chest cavity. We can see our lungs inside, and then the floor of the thoracic cavity is the diaphragm. Okay? So right now, the pressure outside of the chest, so outside of us, that's atmospheric pressure. And atmospheric pressure, remember, is the pressure of the Earth's atmosphere around us. That is not going to change. So the pressure around us is atmospheric. The pressure inside the chest is known as the intrapulmonary or alveolar pressure. This is the pressure in the lung at the alveoli. So when we're talking about pressure in the chest, that's what we mean, the intrapulmonary pressure, the pressure in the lung at the alveoli. So to determine which way air will flow into your lungs or out of your lungs, we have to compare the pressure outside to the pressure inside. And that's going to help us figure out how air flows. So we're going to continue on that in just a second. But what's happening here in this picture, we're zooming in right in this area here and blowing that up. We can see the lung here. We see the visceral pleura, which is the membrane we discussed before, that covers the outside of the lung. Here's our rib cage and rib muscles, the intercostal muscles. And the lining of the rib cage, or the thoracic cavity, we have the parietal pleura, and these two pleura are producing pleural fluid. So this is pleural fluid here. And pleural fluid actually creates a suction between the lung and the inside of the rib cage. Just like when you are at a restaurant and you have a glass with a beverage and ice in it, and the outside of the glass gets nice and sweaty with condensation, that condensation drips down and collects at the bottom of that glass. So if you've ever picked up a glass at a restaurant and the coaster is attached to your glass, that's kind of the same as this suction between the lung and the rib cage. So when the rib cage goes out, the lung will follow because the lung is suctioned to the rib cage, just like that glass is suctioned to the coaster or to the table. So looking down here again, it says that the pressure outside the chest, which remember is our atmospheric pressure, is equal to the pressure inside the chest, which is called intrapulmonary pressure. So since these pressures are equal, air will not flow. So this is between breaths, like when we are not taking a breath or exhaling a breath. This is in between breaths. The muscles are nice and relaxed. No air is moving. Now here, we are getting ready to inhale. Now remember Boyle's law. If volume goes up, pressure goes down, and if volume goes down, pressure goes up. So here we have the rib cage elevating, like it does when we breathe in, and the diaphragm contracting, which means it's going to pull down. So if we look at this picture here, and let's compare it to this picture here, you see the diaphragm relaxed, and now look at it contracted. It has pulled down. When the diaphragm pulls down, this will increase the volume of the thoracic cavity. So now we have more room in the chest. When the volume goes up, remember what happens to pressure. Pressure goes down. So now pressure is less inside the chest than it was before. Atmospheric pressure, on the other hand, never changed. It's still the same. But the chest pressure went down. So now the pressure outside, or atmospheric pressure, is greater than the pressure inside the chest. Because pressure outside is greater than inside, this will push air into the lungs. We inhale. So it summarizes that for us right here. The elevation of the rib cage and contraction of the diaphragm increase the volume of the thoracic cavity, so pressure will go down. Since pressure is less in the chest, air flows in. That's our inhalation. Now, oppositely, when we exhale, the rib cage drops down to its original position and the diaphragm relaxes. So in this picture, the diaphragm is going from, remember when it was contracted when we were breathing in? It's now relaxing, so it's going to be pushing up on the lungs. When the diaphragm relaxes, the volume of the chest cavity decreases. When volume decreases, according to Boyle's law, pressure goes up. So now pressure is higher in the chest than it was before. Remember that atmospheric pressure isn't changing, but the pressure in the chest is higher. So pressure outside, which is atmospheric pressure, is less than the pressure inside, which is our intrapulmonary pressure or chest pressure. So air will be forced out. And that's summarized here as well. When the rib cage returns to its original position and the diaphragm relaxes, the volume of the thoracic cavity goes down. Pressure goes up. Air moves out. So that is exhalation. The primary respiratory muscles, as we just saw, are the diaphragm and the external intercostals. So going back here, we know what the diaphragm is at the floor of the thoracic cavity, and then in between the ribs we have the intercostal muscles. So here are the external intercostals in this picture between the ribs. Now when we are forced breathing, for example, when we're upset or emotional or nervous, we might include some accessory muscles. We might add some other muscles in, and this is going to cause the chest to heave more. The mechanics of breathing are that inhalation is always active, but exhalation can be active or passive. Muscles used in inhalation. So we saw this. The diaphragm contraction draws air into the lungs. It contributes 75% of normal air movement. The external intercostals we just pointed out are going to assist in inhalation as well and contribute about 25% of normal air movement. Accessory muscles will assist in elevating the ribs. Muscles like the sternocleidomastoid, scalenes, pectoralis minor, and the serratus anterior. So let's look at a few of these if we have them in our drawing. So here are the scalenes, sternocleidomastoid, pectoralis minor, and serratus anterior. So those are all going to pull on the rib cage when we have more active or forced breathing to make the chest move even more dramatically. So this is a frontal view of those same important muscles. We can see the diaphragm underneath, the serratus anterior here, pectoralis minor, scalenes, sternocleidomastoid, and the external intercostal muscles as well. Respiratory movements are classified by pattern of muscle activity. So we have quiet breathing and we have forced breathing. Forced breathing first is also known as hyperpnea. This is going to involve active inhalation and exhalation, and this is when we're going to be using those accessory muscles that we just pointed out previously. Quiet breathing, or eupnea, is going to involve active inhalation and passive exhalation. Diaphragmatic breathing, or deep breathing, is dominated by the diaphragm. Costal breathing, or shallow breathing, is dominated by rib cage movements. Intrapulmonary pressure, which we just mentioned, is also called intraalveolar pressure, And the difference of it from the atmospheric pressure determines the direction of airflow, which we just covered. And then we talked about, remember the suction between the two pleura, the parietal and visceral pleura, and that fluid, that suction like the glass in the coaster. The pressure in the space between the parietal and visceral pleura is called the intrapleural pressure. Compliance is a measure of how expandable the lungs are. Lower compliance requires a greater force for you to be able to fill the lungs. Some factors that can affect the compliance include the connective tissue of the lungs, the level of surfactant production, and how mobile your thoracic cage is. Respiratory rates and volumes. So your respiratory system will adapt to changing oxygen demands by varying how many breaths that you take per minute, which is your respiratory rate, and the amount of air that you move in each of those breaths, which is known as the tidal volume. The respiratory minute volume is the amount of air you move per minute, and you can calculate it by multiplying your respiratory rate by your tidal volume. And this will measure your pulmonary ventilation. Pulmonary volumes, like the tidal volume, is again the amount of air you move into or out of the lungs in each breath. Gas exchange occurs between the blood and the alveoli. So we talked about how the alveoli and the blood vessel, the capillary bed, were fused at their basal lamina, and this is going to allow oxygen and CO2 to diffuse very quickly. But gas exchange can also depend on the partial pressure of the gases involved and the diffusion of molecules between gas and liquid. So partial pressure we're going to cover a little bit more. But reminder that partial pressure is the pressure of one gas in a mixture of gases. The diffusion of gases. So the diffusion of gases will occur in response to concentration gradients of those gases. The rate of diffusion can depend on physical principles or gas laws like Boyle's law, which we mentioned before, and we saw how that could determine which way things were moving. Partial pressure, again, the pressure contributed by a single gas in a mixture of gases. In the air we breathe, nitrogen is about 78.6%, oxygen 20.9%, water vapor 0.5%, and carbon dioxide 0.04%. So when we breathe air in, we're not just breathing in oxygen, we're bringing in other gases as well. But the oxygen is what we really want and what we really care about. So the reasons for efficiency of gas exchange include differences in partial pressure across the blood-air barrier are very substantial. So down in the alveoli, if we've got a lot of oxygen in the alveoli and very little in the blood, diffusion will take place very easily. Remembering that diffusion is when we go from a high concentration of a substance to a low concentration. The distance involved in gas exchange is short, and oxygen and CO2 are lipid soluble, which is important because we need to diffuse across the oily surfactant. Total surface area is large. We've got that as well. 150 million alveoli per lung ought to cover it. Blood flow and airflow are coordinated. So remember, blood and airflow connect or meet up in the lungs. External respiration. So blood arriving in your pulmonary arteries has low oxygen and high CO2. This concentration gradient will cause oxygen to enter the blood and CO2 to leave the blood because of diffusion. This rapid exchange will allow the blood and the alveolar air to reach equilibrium pretty quickly. So taking a look at this figure, here's our alveolus, and you can see where the blood-air barrier is. This is where the two membranes are fused. We have really close contact. So we can see the partial pressure of oxygen right now is 100 in the alveolus, and the partial pressure of CO2 is 40 in the alveolus. So here comes deoxygenated blood, and we can tell that by the blue shading. Right now, the partial pressure of oxygen is 40, and the partial pressure of CO2 is 45. So let's compare the partial pressure of oxygen first. So in the alveolus, it's 100, and in the blood, it's 40. So according to diffusion, things flow from a high to a low concentration, so oxygen will diffuse naturally into the blood, oxygenating it, as represented by the red shading. CO2 is 45 in the blood and 40 in the alveolus, so according to diffusion, CO2 will diffuse from the blood into the alveolus to be exhaled. So that gets rid of the CO2 and allows us to gain the oxygen. Now the other part, internal respiration, once we bring that oxygenated blood to our tissues, which are represented by these cells, we then compare the partial pressure of oxygen, which is 95, to the partial pressure of oxygen in the cells or tissues, which is 40. So according to diffusion, we will go from high to low, so oxygen will flow into the tissues, making them very happy. We compare CO2, which is 45, to the CO2, or in the tissues, to the CO2 in the blood, which is 40. So we're going to diffuse high to low. So CO2 diffuses into the bloodstream. We are now deoxygenated. So we are going to carry this deoxygenated blood back to the heart and lungs, and then start this process again. Blood plasma cannot transport enough oxygen or CO2 to meet your physiological needs. So your red blood cells, or RBCs, are going to help by transporting oxygen to and CO2 from peripheral tissues. They're going to remove oxygen and CO2 from plasma, allowing gases to continue to diffuse into the blood. So what does the O2 bind to on the red blood cell? The O2 will bind to iron ions in the hemoglobin molecules in a reversible reaction. So when our O2 binds to the iron in hemoglobin, this will form oxyhemoglobin. Each red blood cell has about 280 million hemoglobin molecules. Each hemoglobin molecule can bind 4 oxygen molecules. Hemoglobin saturation is the percentage of heme units containing bound oxygen at any given moment. So there are some factors affecting hemoglobin saturation. The partial pressure of oxygen in the blood. If the PO2 increases, hemoglobin will bind oxygen. If the PO2 decreases, hemoglobin releases oxygen. So that's the partial pressure of oxygen of blood. If the PO2 increases, hemoglobin binds oxygen. If the PO2 decreases, hemoglobin releases oxygen. Blood pH. As the pH goes down, saturation of oxygen declines. Temperature, we want our temperature to be around 98.6 to carry oxygen at most efficiently. And metabolic activity within the red blood cells, which we'll go a little further on in just a bit. So when your temperature increases, hemoglobin releases more oxygen. When temperature decreases, hemoglobin holds oxygen more tightly. Temperature effects are significant only in active tissues that are generating large amounts of heat, like your skeletal muscle. Hemoglobin and BPG. So BPG stands for the biggest word ever, bisphosphoglycerate. Maybe not the biggest word ever, but it's pretty big, bisphosphoglycerate. So red blood cells generate ATP, which is energy, only by glycolysis, forming bisphosphoglycerate or BPG. BPG will affect your oxygen binding and release. More BPG, more oxygen released. BPG levels rise due to an increase in pH or certain hormones. If BPG levels are too low, hemoglobin will not release oxygen. Fetal hemoglobin is a bit different from adult hemoglobin. The structure differs, and at the same partial pressure of oxygen, fetal hemoglobin will bind more oxygen than adult hemoglobin. This will allow the fetus to take oxygen from mom's blood. CO2 and how it's transported. CO2 is generated by aerobic metabolism. CO2 in your bloodstream can be carried in 3 ways, and we're going to look at these 3 ways. It can be converted to carbonic acid. It can be bound to hemoglobin within red blood cells, or it can dissolve in the plasma. 70% of CO2 will be transported as bicarbonate ions. And we get that bicarbonate by breaking down carbonic acid. So we've got some commentary here, but let's go back, or let's go forward and let me show you this in a picture, and then we'll go back to the commentary. So here's our CO2, 100% of CO2 at this time. 7% dissolves in the plasma. This means that 93% will diffuse onto the red blood cell. 70% of that 93% will be converted to carbonic acid, which is H2CO3. We're going to break up that acid. So it will dissociate into H+. We're going to pull off one of those H's into H+, and HCO3-, which is bicarbonate. That HCO3- will be kicked into the plasma in exchange for a chloride. That's called the chloride shift. The H+ we pulled off will be buffered by hemoglobin. Again, 70% converted to carbonic acid, H2CO3. We break carbonic acid up into H+ and HCO3-. HCO3- is kicked into the plasma in exchange for a chloride. The H+ will be buffered by hemoglobin, which leaves 23% that will bind directly to hemoglobin, forming carb-amino hemoglobin, or HbCO2. So these are the 3 ways that we will transport CO2. Okay, so that should be written out here. 70%, we saw this, is transported as bicarbonate. Most CO2 enters bloodstream, diffuses onto red blood cells, and the CO2 is converted to carbonic acid, H2CO3. We break that up into H+ and HCO3-. Hydrogen binds to hemoglobin to be buffered, and bicarbonate, which is the HCO3-, will move into the plasma in exchange for a chloride, the chloride shift. 23% is bound to portions of hemoglobin molecules forming carb-amino hemoglobin. 7% is transported as dissolved gas molecules in plasma. So here's a summary of oxygen pickup. So here's our alveolus, here's our capillary bed, here's our plasma, and our red blood cell. We breathe in, oxygen is high in the alveolus, low in the red blood cell, so oxygen diffuses right onto the red blood cell and binds to hemoglobin. Hemoglobin will carry that oxygen to the tissues. Here they are over here. And the oxygen, because it's high in the blood, low in the tissues, oxygen will diffuse right into the tissues, making them very, very happy. The tissues then say, hey, red blood cells, can you take out our trash? We want to get rid of this CO2. So CO2 will diffuse into the blood because it's low in the blood, high in the tissues. 7% dissolves in the plasma. 93% goes on to the red blood cell, remember. 70% becomes carbonic acid, which we break up into H plus and HCO3 minus. HCO3 minus kicked into the plasma in exchange for a chloride. Hemoglobin buffers the hydrogen ion, and 23% will bind directly to hemoglobin. Okay, and what's left? A lot of that 23% will move from the red blood cell into the alveolus, where you will then exhale it out into your environment. The respiratory center of the brain. When oxygen demand rises, your respiratory rates increase. You have voluntary and involuntary components of this, so you can control right now. If you want to breathe really, really, really deeply, really fast, really slow, you can make that decision. But it also happens involuntarily when you get upset, or if you're really, really relaxed or nervous. Those things can all make a difference with your respiratory rate. Strong emotions can stimulate respiratory centers in the hypothalamus. Your emotional state can also activate sympathetic or your parasympathetic division of your autonomic nervous system, which can cause either bronchodilation, where the bronchi become larger in diameter, or bronchoconstriction, where they become smaller in diameter. Anticipation of exercise can increase your respiratory rate and your cardiac output by sympathetic stimulation or fight or flight. Changes in the respiratory system in newborns. Before birth, the pulmonary vessels are collapsed, so the lungs contain no air. Because a fetus, of course, is suspended in amniotic fluid, so breathing in wouldn't make sense. It'd be like you trying to breathe underwater. During delivery, the placental connection is lost. Blood PO2 falls, and PCO2 rises. So at birth, the newborn overcomes the surface tension to inflate the bronchial tree and the alveoli and take the first breath. Subsequent breaths will fully inflate the alveoli. Effects of aging on your respiratory system. Elastic tissue will deteriorate around the alveoli. This can alter lung compliance. Arthritic changes in the chest can restrict chest movements and limit the respiratory minute volume. Emphysema affects individuals over the age of 50, and how bad it is depends on your exposure to respiratory irritants like cigarette smoke. The goal of respiratory activity is to maintain homeostatic oxygen and CO2 levels in peripheral tissues. Requires coordination between your respiratory and cardiovascular systems. So this concludes Chapter 23. We'll see you again in Chapter 24, the digestive system.